I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss the question bank on module 5 in the course Engineering Physics, that is harmonic oscillations and waves in one dimension. So first let us look at the short answer questions. When can we call a body in motion to execute a periodic motion? Define it. Means in short, we are going to define periodic motion. So what is periodic motion? When the motion of the body repeats itself after regular intervals of time. The motion of the body is repeating after regular intervals of time. Then we say it is periodic motion. So now if you see a simple pendulum, this is the equilibrium position. When you take it to one extreme and leave it, so the pendulum keeps oscillating like this about the equilibrium position, and the motion is periodic, means it repeats itself in regular intervals of time. Then you say it is periodic motion. Now coming to simple harmonic motion. What is simple harmonic motion? It is the simplest example of oscillatory motion. So simple harmonic motion is oscillatory motion. So when an object moves to and fro along a straight line, it performs simple harmonic motion. So all examples of oscillatory motion are examples of simple harmonic motion. Here I'll give you one example of the needle of a sewing machine. Needle of a sewing machine. So you must have seen the needle, how it moves up and down about a fixed point. So the motion is along a straight line in the vertical direction, but it is oscillating about a fixed position. So you call it as simple harmonic motion. Now define the terms amplitude and time period. So what is amplitude and what is time period? So to understand that, we will consider the motion of an object which is suspended with the help of a spring. So this is the mass M. Suppose we just pull this mass down and leave. Then what happens? The mass will keep oscillating up and down like this about the mean position, if this is the mean position. Now when it is oscillating, if we can trace the positions of this object. So at time t is equal to 0, you start from here at one extreme position at time t is equal to 0. So after t by 4 seconds, it comes to the equilibrium position. And after t by 2 seconds, it comes here, and so on for one complete interval. If you can trace the position of this object, you will get a curve like this. So if you see here, the maximum displacement in the upward direction or in the downward direction, we call it as amplitude. So here this is the amplitude and here this is the amplitude, and it is generally denoted by capital A. Then what is time period? The time taken to complete one oscillation. What is the time it takes for one complete oscillation? We call it as time period. Now if you see this motion, I will consider this is one complete motion, or if you start from here, this is one complete motion. So what is the time it takes starting from here and here? This is the time t. So we are calling it as t. And to find t, we have a formula. T is equal to 2 pi under root m by k, where k here is the spring constant. It depends upon the spring constant also. So T is equal to 2 pi under root m by k. M is the mass and k is the spring constant. Now coming to the next set of questions. Define phase of a body. Write the expression for the velocity of a body. And define the frequency of a body executing simple harmonic motion. So we will discuss these three questions now. What is phase? Phase specifies the angular displacement as well as the direction of the point executing simple harmonic motion. So it specifies the angular displacement as well as the direction of the point executing simple harmonic motion. So theta is equal to omega t. So if you have to remember this, if you remember the basic formula for angular velocity, omega is equal to theta upon t. So theta is equal to omega t. So that is how we are defining the phase. Now the expression for velocity. The velocity can be found by differentiating the displacement. So we know we have denoted the displacement x by a cos omega t plus phi when the body is starting from the extreme position. A cos omega t plus phi. Now if you want velocity, velocity is what? It is the rate of change of displacement. Dx by dt. So I am going to take the derivative of x with respect to t. So the derivative of cos is minus sign. So we have minus a sine omega t plus phi. And for omega t we get omega. So we get minus a omega sine omega t plus phi. So what we are getting here for the velocity, the expression for velocity is given by minus omega a or a omega. Both are correct. Sine omega t plus phi. So this is the expression. And if we have to find the velocity, we also use the formula v is equal to omega under root a square minus y square. If you are going to derive the expression for v, we use v is equal to omega under root a square minus y square. From here, we are getting the values of v maximum and v minimum. When is the velocity maximum? At y is equal to 0. Means at the mean position, v is maximum. V is v maximum. So put y is equal to 0. So under root a square is a. So v is equal to a omega. Or I can say v max is a omega. So this is the formula for maximum velocity. Next, define frequency. So what is frequency? The number of oscillations made per second is known as the frequency. And frequency is given by 1 upon t. F is equal to 1 upon t. We have already seen the formula for F. F is equal to 1 by t. And in place of t, we are substituting 1 by 2 pi under root m by k. So we can also write it as 1 by 2 pi under root k by m. So this is the formula for frequency. Then how we are going to understand this frequency? How it depends upon the time period. Now suppose t is equal to 4 seconds means the time it takes to complete one oscillation is 4 seconds. So what is the frequency? What is the number of oscillations it makes per second is only 1 by t, that is 1 by 4. So it completes only 1/4 cycle. Now if we see the other way, if the time period is 1 second means it takes 1 second to complete one oscillation. So what is the frequency? 1 by 1, that is 1. So the frequency is 1. Frequency means what? The number of cycles made per second. So in 1 second, how many cycles it is making? 1. So this is how we try to relate frequency and time period. First, we are going to define the characteristics of simple harmonic motion. So what are the characteristics? First thing is it should have a restoring force. There should be a restoring force that acts on the system to bring it back to the equilibrium position. And the second one is inertia. Inertia here means it is the inability of the body to change its state by itself, whether be it in motion or be it at rest. So the system should have inertia. and this should be on a frictionless surface. So if there is friction, there is so much loss of energy. So these are the three important characteristics of a simple harmonic motion. Next, distinguish between free and forced vibrations. What are free vibrations and what are forced vibrations? So in free vibrations, what is the phenomenon that is happening? The body is displaced from its equilibrium position and it is released. Then the restoring force that acts on the body may set it into vibration. Because of the restoring force, the body will keep on oscillating about the mean position, and such vibrations we are calling as free vibrations. So this is what we see in free vibrations. Now in forced vibrations, what is happening? The vibrations of the body under the action of an external periodic force. So there is a periodic force that is applied on the system, and because of which the body vibrates, and the body vibrates with the frequency equal to the frequency of the external periodic force. Whatever periodic force we have applied, the body will start oscillating with that particular frequency. So then we call them as forced vibrations. Now coming to the frequency. Frequency is called the natural frequency here because it depends upon the frequency of the oscillation. It depends on what? Mass, dimensions, elastic properties and mode of vibration of the vibrating body. It entirely depends upon the object or the body that is in motion, its mass, its dimensions, its elastic properties and the mode in which it is vibrating. Here the frequency is equal to that of the external periodic force. So whatever periodic force we are applying, the object will vibrate with that particular frequency. So now if you see, what is the best example for free vibrations is simple pendulum. So in case of a simple pendulum, you just take it to one side and leave. It keeps on oscillating with its own natural frequency. Now for forced vibrations, it is the vibrations of the pendulum in a clock. So these are controlled or forced vibrations. So the example here is the pendulum of a clock. Now coming to the damped harmonic oscillator. So when we talk about damping, damping means the forces that act on the system opposite to the direction of motion of the object. So whenever we are talking about oscillations, the object is released from its mean position. I take the example of simple pendulum, we take it here and leave. So then what happens? It will start oscillating. Like this, it will continue oscillations. But now, whatever medium in which this object is, that offers some resistance to the motion of this object. And we are calling them as damping forces. And an oscillator on which there are damping forces, we call it as damped harmonic oscillator. Now we are going to discuss what are the two forces that act on a damped harmonic oscillator. So they are, one is the frictional force and the other is the restoring force. We have already discussed for a body which is in oscillation, in simple harmonic motion, the restoring force is required. So you see here in this case, where we have taken an object which is attached to a spring and it is suspended. Suppose here we consider there is air, there is no liquid or anything present, it is suspended in air. So how is the object coming back to the equilibrium position? Because of the force F, which we call as the restoring force, which tries to bring it back to the normal position. Now on this, also we have a damping force. What is a damping force? It's a resistive force that acts on the object and acts in the direction of opposite to the motion of the object. So we have one is the restoring force and the second is the damping force or the frictional force. So the frictional force and the restoring force are acting in case of a damped harmonic oscillator. Next, what is the definition of the term wave motion? So what is wave motion? What are the characteristics of wave motion? Next question. Then compare three different types of damped oscillations. So in damped oscillations, we are going to have three different types. So we are going to discuss all the three different types of oscillations. So first one, what is wave motion? What is wave motion? It is the transfer of energy and momentum from one point of the medium to another point without the actual transport of matter. This is very important. The particles only vibrate about the mean position, but the energy is being transferred from one point to the other point. Then we call it as wave motion. Means the energy is transferred in the form of waves. Now, what are the characteristics of wave motion? Because when we say wave motion, again the particles are in simple harmonic motion. So whatever characteristics we have discussed for simple harmonic motion, here also the same thing is applicable. So the medium should have elasticity. Means there should be a restoring force we were talking about. So that force, the medium should have elasticity so that it will try to bring it back to the normal position. Then inertia, the property by which it cannot change its state by itself. Then there should be a little frictional force to avoid dissipation of energy. If there is no frictional force at all, then what happens? The body will slide over. So we need little frictional force. If the frictional force is more, then the damping will be more. The object may not oscillate for a longer time. Now consider the different cases of damped harmonic oscillators. Depending upon the values of B and omega, which are constants, there are three possible cases. What are the three possible cases? The first one is underdamped. In underdamping, what happens? The system oscillates with the amplitude gradually decreasing to 0. In underdamping, we are not considering any effect of the resistive forces. So, when we are talking about the oscillation of a simple pendulum, so when we disturb the object from this position, take it to one extreme, it will move like this and come back. And we assume that the oscillations will continue for an infinite time. They will not come to rest. So the system oscillates with the amplitude gradually decreasing to 0. So what happens? After certain time, they will die off. Then comes the overdamping. So in overdamping, the system returns to equilibrium without oscillating. If the damping on the system is more, damping forces are more. So when we displace the object from its mean position, it will simply come to rest and stop without oscillating. So that is overdamping. Then what is critical damping? The system returns to equilibrium as quickly as possible. That is the main difference between overdamping and critical damping. In overdamping also, it comes to rest without oscillating. In critical damping also, without oscillating, it comes to rest. But here, in critical damping, we want the system to come to rest as quickly as possible. Now the next one, what are the forces which act on a body executing forced vibrations? Now we are going to talk about a forced harmonic oscillator. So what are the type of forces that act on these type of oscillators? And then we will also see the phenomena involved in a stationary wave, means how are stationary waves formed. And then the phenomena involved in progressive waves. So we are going to understand about progressive as well as stationary waves. So first let us see what are forced vibrations. So the forces acting upon a particle of a forced oscillator are the frictional force, the restoring force, and the applied external periodic force. Whenever we are saying it's a forced oscillator, there is an external periodic force that is acting on the system. So this is the external periodic force. And then for the body to oscillate, to continue oscillating, there should be a restoring force. So this is the restoring force. And there should be a frictional force for the object not to slide or to maintain its oscillations. Next, what are standing waves? How are standing waves formed? They are produced due to superposition of two identical progressive waves. So when I say identical, they should have the same amplitude and frequency. We have already discussed the definitions of these two. Amplitude is the maximum displacement and frequency is the number of vibrations per second. So the two waves we are considering should have the same amplitude and the same frequency. They should move along the same line but in opposite direction. So if you see the example here, if I have a wave going from A to B, now another one coming from B to A, they are of the same frequency and same amplitude, traveling along the same line but in opposite directions. So they are standing waves. So this is how standing waves are formed. So the best example is a string which is tied at both the ends. If you just pluck the string and leave, then what happens? You will see stationary waves. Then progressive waves. What are progressive waves? They are produced due to continuous periodic vibrations of the particle. So here in a progressive wave, there is continuous vibration of the particles and the wave proceeds forward into the medium and will never return back. Then we call it a progressive wave. So the vibrations of the particles are continuous. Now the next question, what are the laws of stretched strings? When it comes to stretched strings, what are the laws that they obey? Then what is a longitudinal wave? Write the wave equation of a longitudinal wave. We have to write the equation also for longitudinal. Then transverse wave and the transverse wave equation. Then finally we will compare the longitudinal wave with transverse wave. First let us see the laws of stretched strings. Now first one is the law of mass. How does the frequency depend upon the mass? So for a string of constant length, we are keeping the length constant, and uniform density and under constant tension, the tension is also constant, the frequency of vibration is inversely proportional to the square root of its mass per unit length. So the frequency is inversely proportional to the square root of the mass per unit length. When I say mu, mu here represents the linear density or the mass per unit length. So what does this relation tell us? If the linear density is more, the frequency will be less. Next one is the law of length. How does it depend upon length? So when we are talking about length, we are going to keep the tension constant. So for a string under constant tension, the frequency of vibration is inversely proportional to the length. So F is inversely proportional to the length. So L here represents the length of the string. So more the length, less the frequency. Frequency here means the number of vibrations. Then law of tension. So when we are talking about tension, we'll keep the length constant, uniform density. Then the frequency is directly proportional to the square root of tension. So we have seen three laws. So in this law, it is directly proportional to the square root of tension. So what the first law says, frequency is inversely proportional to the square root of linear density or the mass per unit length. The law of length says that frequency is inversely proportional to the length of the string. And the third law says frequency is directly proportional to the square root of tension. So how do we combine the three laws? So if you have to write the formula for F, F is proportional to 1 by L under root d by mu. If you remove the proportionality sign, and in case of a transverse wave, we get F is equal to 1 by 2L under root d by mu. So this is how we get the formula for frequency. The frequency of the stretched string is given by F is equal to 1 by 2L under root d by mu. Now, what is a longitudinal wave? The particles of the medium vibrate about their equilibrium position in a direction parallel to the direction of propagation of the wave. So, let us see the example here. So, we are talking about a longitudinal wave. So, this is the string we have considered, and these red balls denote the particles of the string. Now, if this is the direction of motion of the wave, this is the direction of motion of the wave. So, how are the particles vibrating about their mean position? So, they vibrate parallel. These two are parallel to each other. So, if the direction of vibration of the particles is parallel to the direction of propagation of the wave, we call it a longitudinal wave. So, in the simulation, you can observe very clearly how the particles are vibrating about their mean position, and the motion is passed on forward, and it is parallel to the direction of propagation of the wave. And then how do we write the wave equation? In case of a longitudinal wave, dou square n by dou x square is equal to rho upon y, dou square eta by dou t square. So, rho here is the density and y is the Young's modulus. So, what we are talking about for a longitudinal wave. Now, define a transverse wave. So, what is the difference here? Particles of the medium vibrate perpendicular to the direction of propagation of the wave. So, whatever the vibration of the particles, the type of wave depends upon the direction of vibration of the particles. So, now you see here, how are the particles vibrating? So, they are vibrating up and down, perpendicular to the direction of propagation of the wave. If the wave is propagating forward in this direction, the particles are vibrating up and down. So, we call it a transverse wave. So, what is the equation for a transverse wave? So, the transverse wave equation is given by dou square y by dou x square is equal to mu by t dou square y by dou t square. So, here mu represents the mass per unit length and t here is the tension in the string. Now, how do we differentiate between transverse waves and longitudinal waves? So, in transverse, we have seen the particles vibrate perpendicular to the direction of propagation of the wave. In longitudinal, they vibrate parallel to the direction of propagation of the wave. This is the first major difference between transverse waves and longitudinal waves, which we have already seen. And then the next one is they consist of crests and trough. Crest is the maximum displacement in the upward direction and trough is the maximum displacement in the downward direction. So, they have a series of crests and troughs. And in a longitudinal wave, there are compressions and rarefactions. There will be a series of compressions and rarefactions which alternate each other. So, what is a compression? When the particles are vibrating parallel to the direction of propagation of the wave, there are certain regions where they come closer together. So, the regions where they are closer together, we call it a compression. So, in the vibration when they are going apart, when the particles are vibrating, when they are going apart, there will be a rarefaction. So, it consists of compressions and rarefactions. Now, coming to the variations in pressure and density, in transverse wave, there are no variations. No variations in pressure and density. They are vibrating individually, perpendicular to the direction of propagation of the wave. But when it comes to longitudinal wave, there are variations in pressure as well as density. Why? Because I told at compressions, the particles come closer together. So when they come closer together, definitely the density is more and the pressure is more. And at the regions of rarefaction, there may be less density. So there are variations in pressure as well as density. Then transverse waves can be propagated through solids and surfaces of liquids only, but not in gases. So we generally say they travel through solids. But when it comes to longitudinal waves, they pass through solids, liquids and gases also. So example here is the light wave. Here it is a sound wave. Now we come to the long answer questions. We are going to discuss long answer questions. So here I am not going to give you the answer. I am just going to outline what are the points that you will have to touch. And for the complete derivation, you can refer to the particular video. If you want the equation for a simple harmonic oscillator, you can just click on the video, simple mechanical harmonic oscillator. You will get the entire description regarding the simple mechanical harmonic oscillator. Then we are also going to summarize the concept of simple harmonic motion and its characteristics. So first let us see the equation. So where do we start here if you are talking about a simple harmonic oscillator? First thing is we have to talk about the forces that are acting on the oscillator. So in case of simple mechanical oscillator, the only force that is acting is the restoring force, which is given by minus kx. F is equal to minus kx. And then we have the Newton's second law of motion gives us F is equal to ma, or A is nothing but acceleration. Acceleration can be written as d square x by dt square. So we get the second equation. Then comparing these two equations, when you compare these two, because the left hand sides are the same, the right hand sides you can equate, and then you are dividing throughout with m, and then you will get this equation where you are substituting for k by m as omega. So d square x by dt square plus omega square x is equal to 0. This is the equation of motion for simple mechanical harmonic oscillator. Now coming to the characteristics, we have already seen the restoring force is directly proportional to the displacement. And then the restoring force is always acting or directed towards the mean position. So you will have to elaborate on this because they are long answer questions. Then explain the terms displacement, velocity, acceleration of a simple harmonic oscillator along with their expressions. You see here, they are asking the expressions also. Now, because it's a long answer question, you are having 3 subparts. Write the displacement. How do you write? Well, first you have to define. Definition will carry 1 mark and the expression will carry 1 mark. So for displacement, if I am talking about the displacement y is equal to a cos omega t minus k. Or if I write in terms of phi, a cos omega t plus phi. So this represents the displacement of the particle. Now if you have to write the velocity, velocity is equal to dy by dt. Velocity is the rate of change of displacement. The velocity here will be given by dy by dt. You can take the derivative of this and write the expression for v. And then for acceleration. Acceleration is nothing but rate of change of velocity. So once you get the velocity, you can get the acceleration. So you will have to write the expressions and also define the terms, explain the terms, and then you may have to mention the units also in which you measure, so that it will be a long answer question. Then show an expression for the potential energy of a simple harmonic oscillator. So we are going to write the expression. You may have to derive it since it's a long answer question. So displacement, we have already seen the definition. The velocity expression dx by dt. Then the expression for acceleration a is equal to dv by dt. Now coming to the potential energy. What is potential energy? First you have to define. It is the energy stored in the spring and it is equal to the work done in extending it or compressing it. When you are taking a spring and you are compressing it, you are doing some work on it to compress it, and the amount of work done is stored in the spring in the form of potential energy. So now we are giving an example here. The work done in extending it from x to x plus dx is kx dx. So the potential energy will be given by integral 0 to x kx dx. So you keep the constants outside. So you can write it as k integral of 0 to x dx. So integral of x dx will be k into x square by 2 within the limits 0 to x. So the upper limit minus the lower limit we do. I can bring 2 also outside, half k x square minus 0. So it gives only half k x square. So this is how you will derive the expression for the potential energy. And how do you write it? For a simple harmonic oscillator, we know the displacement is given by x is equal to a cos omega t plus phi. So if you substitute here, you have a square cos square omega t plus phi. This is the expression for potential energy. Next, find an expression for the kinetic energy of a simple harmonic oscillator. So how do we get the kinetic energy? We know the basic formula for kinetic energy is half mv square. So once you know the formula, you have the expression for V. What is the expression for V? V is equal to minus a omega sine omega t plus phi. So take the square of it and substitute it here. Half m into V square will be a square omega square sine square omega t plus phi. So this is the expression for the kinetic energy. Now, if we are talking about both the kinetic as well as potential energy, kinetic energy is given by half m omega square a square sine square omega t plus phi, and potential energy is given by half k a square cos square omega t plus phi. If you want the total energy is always the potential energy plus the kinetic energy. So we are going to get the total energy. So we have U, we have K, then the total energy is given by the sum of the two. So what we get here is half K A square. Next, show the differential equation of a damped harmonic oscillator and illustrate the conditions of different types of damping. We also have to explain the conditions. So first writing the equation, differential equation, then explaining the conditions. The definition may carry 1 mark for damped harmonic oscillator, and then the expressions and the conditions, 2 marks each for 3 different conditions. So we will see what is a damped harmonic oscillator. First, we are going to define the damping force. It is proportional to the velocity and is always directed opposite. So Fd is equal to minus gamma V. Gamma is the damping coefficient we say. So minus gamma dx by dt. So gamma depends upon the properties of the medium, and here in case of damping we are having 2 forces. One is the damping force and the other is the restoring force. F is equal to minus kx. But if you want the net force, it will be the sum of the 2 forces. So the net force F is equal to the restoring force plus the damping force. And then derive the expression by equating it with the Newton's law. According to Newton's law, F is equal to ma. So now ma should be equal to minus kx minus gamma v. So substitute for a d square x by dt square, and then for v dx by dt, and bring all the terms onto one side. So this describes the motion of the block. Now we will discuss the conditions. So what will be the final expression we write is this: d square x by dt square plus 2b dx by dt plus omega square. So what does b represent here? B represents gamma by 2m, or 2b is equal to gamma by m. and omega square is equal to K upon M. Now first case 1. Case 1 is underdamping. In underdamping, what is happening? B square is less than omega square. So the system oscillates with the amplitude gradually decreasing to 0. So in underdamping, we have already seen that the amplitude gradually decreases to 0. So there is a small amount of damping because of which there are resistive forces acting and the body is coming to rest. So this occurs because the non-conservative damping forces removes energy from the system, and that is usually in the form of thermal energy. That is why the system slowly comes to rest. Now, what is the condition for critical damping? So, in critical damping, what we have seen, the system comes to rest without oscillating, but as quickly as possible. So, what is the condition for that? B square is equal to omega square. If B square is equal to omega square, the system returns to equilibrium as quickly as possible without oscillating. Now this will be the graph for oscillation. It will come to rest within a very short time and it does not oscillate. Now the third one is overdamping. What is the condition for overdamping? B square greater than omega square. Then it is overdamped. In overdamping also there are no oscillations, but more slowly it comes to rest depending upon how overdamped it is. So these are the three conditions you will have to mention along with the definitions. So now coming to the graph, how do you represent it in the form of a graph? So if you see for overdamping, first one is overdamping. If the overdamping is very high, you can see the green line. Means it is not oscillating. It will come to rest, but not so quickly. It will take time. Okay. Then the second one is critical damping. In critical damping also it does not oscillate, but it comes to rest very fast, very quickly. So here the red line denotes the critical damping. You see here, it is not oscillating, no oscillations, but comes to rest very quickly. Here it is taking time, very slowly. The third one is underdamping. In underdamping, what happens? The system keeps on oscillating. So these are the three different cases for damped harmonic motion. Now we are going to talk about underdamped harmonic oscillator, how the graph is going to be. So in underdamping, what we have seen, the system will keep on oscillating. So what happens if you gradually increase the amount of damping? The period and frequency begin to get affected because the damping opposes the motion of the object and hence it slows down and brought to rest. So for example, if you are keeping an object or a mass kept immersed in a liquid, okay, a less viscous liquid, then what happens? It will oscillate and slowly come to rest. Now coming to critical damping, what is the graph? So damping in which there are no oscillations and it will quickly come to rest. So here you see it's not oscillating but coming to rest very fast. Within very short time it is coming to rest. Now in overdamping also we have highly overdamped and slightly overdamped. Overdamped means no oscillation. It will come to rest but not so quickly. So here what we are seeing is the motion of an overdamped system is non-periodic. This is one thing we have to understand about overdamping. It is non-periodic, means it may not repeat after regular intervals of time. So regardless of the initial conditions. So larger the damping, longer the time to decay. If the damping is more, so then the time to decay, the oscillations is also more from the initial disturbance. Next, discuss the oscillations and amplitude of variation with respect to force to frequency. in case of a forced damped oscillator. So we have to only talk about forced oscillations. So derive the expression for forced oscillation. So whatever we have seen for damping, now you will also have the force. You will equate it to F naught sine pt and then derive the expression. Next, explain the term wave motion. We have already described where the particles vibrate about the mean position. The energy and the momentum are being transferred. And then you also have to explain the characteristics and the properties. So it becomes a long answer question. Then 11th one, find the equation of motion for a plane progressive wave. So here in a progressive wave, what we have seen, it progresses forward into the medium and will never come back. So first you will have to write the expression and then explain the terms. Then discuss various types of waves and the propagation mechanism of transverse and longitudinal waves. So two types of waves. We'll do the broad classification in mechanical waves. We have transverse as well as longitudinal depending upon the mode of vibration. So they're talking about the propagation mechanism. How are the particles vibrating and how the wave is being propagated in the forward direction. Next, what is a transverse wave? Derive the expression. So we have already seen the particles vibrate perpendicular. Or we also have seen the expression dou square y by dou x square is equal to under root mu by t dou square x by dou t square. So whatever equation, I'll show you the equation. Dou square y by dou x square is equal to mu by t dou square y by dou t square. So this expression you will have to derive because it's a long answer question. First you will define what transverse wave is. You will write the expression and you will derive all the steps. Now what are reflection and transmission of waves and their coefficients? So when we have to write, we will have to derive the entire derivation. First, we are going to take a wave at the boundary. How the wave is getting reflected. We will take this as at x is equal to 0. So what are the forces that are acting? The tension that is there in the string. And derive the expression for AR upon AI will give us the reflection coefficient. This is the reflection coefficient. So it all depends upon the impedance in the system. Z1 is the impedance on the wave traveling in the forward direction and Z2 is traveling in the opposite. So Z1 minus Z2 upon Z1 plus Z2 will give the reflection coefficient. Now what is the transmission coefficient then? The transmission coefficient is given by AT upon AI, which is equal to 2Z1 upon Z1 plus Z2. So this is known as the transmission amplitude coefficient and is also denoted by T12. Next, what is a longitudinal wave? Derive the wave equation. So we have already seen particles vibrating parallel to the direction of propagation of the wave. And the wave equation is given by dou square eta by dou x square is equal to rho by y dou square eta by dou t square. So you will have to derive the expression starting from the displacement and how the forces act, how the layers are getting displaced, what will be the Young's modulus, everything you can refer to the video on the expression for longitudinal wave and then get this expression. Next, find the velocity of the transverse wave propagation along a stretched string and obtain the frequency of vibration of a stretched string of length L. So, velocity means we have V is equal to under root T by mu. And then you also have to derive the expression for frequency. We have seen 1 by 2L under root T by mu. So you should keep on writing all the three laws, combine them and get the expression. Then explain the terms periodic motion, oscillatory motion, damped and undamped oscillation, forced oscillation. So 5 definitions. We have already defined all in our short answer questions. You will combine all of them and write. Now compare how progressive waves are different from stationary waves. So we are going to compare the two. Then explain longitudinal wave, transverse wave, progressive wave and laws. So all the four you will have to explain. Now coming to analytical questions. Analytical questions are problem solving questions. So first you will have to analyze what is given in the question and what you have to find. I'll just give you the brief outline. For all the solutions in a detailed manner where it is explained, you can refer to the numericals on module 5, that is harmonic oscillations and waves in one dimension, where we have all solved all these numericals. So the first one, what is the data given? The time period is given. The amplitude is given. We have to find the maximum acceleration and maximum velocity. So first we will write the data given and what we have to find. These are the two things that we have to find. So which formula we are going to use? First we will have to find omega, because we know the formula for Vmax and Amax. So Vmax is A omega, Amax is omega square A. Amplitude is given. We don't have omega. So using this formula, we'll first find omega because the time period is given, and then substitute and get A max and V max. So what is omega? 2 pi by t. So it will be 0.628 radian per second. Now substitute this in the formula first for V max, A omega. A is 1.5, omega is 0.628. Just multiply and write the answer. A max is omega square A. Omega we have got, A we know. Substitute, write the answer along with the units. Velocity is in meter per second. Acceleration is in meter per second squared. Now the second one. A body executing simple harmonic motion has a velocity. So the velocity is given. It goes 1 centimeter on either side. So what is this? This is the amplitude, maximum displacement from the mean position. So 1 centimeter on either side of the mean position. Calculate the time period. We have to find the time period. So write the data given first. V max is given, A is given, T we have to find. Which formula we'll use? We know the formula for V max. Omega is equal to 2 pi by t. So T is equal to 2 pi by omega. V max is equal to A omega. So omega will be V max upon A. So how we are getting omega is, we are writing the formula in terms of known values. V max we know, A we know. So we are writing it in known terms and getting omega. So once we get omega, we can find the time period by substituting it in the formula. T is equal to 2 pi by omega. So let us see how we are doing. So omega, V max upon A, just the substitution, 16 upon 1. So omega is 16 radian per second. So what is the time period? 2 pi by omega, 2 into 3.14 by 16. That gives us 0.3925 seconds. So these are the steps you have to follow. First, identifying or analyzing the question given, writing the data and what we have to find, using the appropriate formula, then substituting and simplifying, writing the result along with the units. That is very important. Now coming to the third question. A body of mass 5 gram, mass of the body is given. An elastic force of 40 dyne per centimeter and a frictional force of 5 dyne second per centimeter is acting on the body. It is displaced through 2 centimeters, means the amplitude is given and then released. Find whether the resulting motion is oscillatory or not. So to find this, first you should know the condition. What is the condition for oscillatory motion? Only in one case the system oscillates, that is in under damping. In critical damping and over damping, it does not oscillate. So let us first check the condition for oscillation, and then you will find the time period of the oscillatory motion. So let us write the data given. M is given, K is given, gamma is given, X is also given. We have to find T. So which formula will be using? T is equal to 2 pi under root omega square minus B square. So how do we get omega square? K by M. How do we get B? Gamma by 2M. Because gamma is given, M is given. K is given, M is given. So both the values we can find and then we can substitute here. So omega square we are getting 8 and B we are getting B square we are finding directly here 0.25. Now what is the condition for oscillatory motion? B square should be less than omega square. So we will first check for this condition to say whether it is oscillatory or not. B square we got 0.25 and omega square we got 8. So definitely B square is less than omega square. So it should be oscillatory. 0.25 less than 8. So it is oscillatory. Now find T. Substitute in the formula. T is equal to 2 pi under root omega square minus B square. Omega square we got 8. B square we got 0.25. So the answer will be 2.25 seconds. Now coming to the next one, fourth one. A 0.5 kg mass suspended from a linear spring of force constant 1000 Newton per meter and a damping coefficient 0.05 Newton second per meter. An external force of F is equal to F naught sin PT is applied, and where F naught is 25 Newton and P is twice the natural frequency. P here is the frequency of the applied force. It is twice the natural frequency of the system. Then we have to calculate amplitude and also the phase shift. Okay. So here we are doing the problem on forced harmonic oscillator. So first write the data and analyze it. What is the data? M 0.5 kg, K force constant 1000 Newton per meter, then the damping coefficient 0.05, then F naught is given 25 Newton and P is twice the natural frequency. So we are writing if the natural frequency is omega naught, so the frequency of the external periodic force will be 2 omega naught. Find A and find phi. Write the formula first. Formula for amplitude A is F naught upon under root omega naught square minus P square plus 4B square P square. This is the formula for amplitude. So how do we get F naught? F naught is not given. We are given capital F naught. So small f naught is equal to capital F naught upon M. So you have F naught, you have M. So we can find out F naught. Then we will find omega naught square because we want omega naught square here, which is K upon M. K is given, M is given. And then we also need B. B is gamma by 2M. The damping coefficient is given. Upon 2M gives us B. So first we will find these values and then get the value of A. So let us find omega naught square. Omega naught square is K by M. Simple. Substitute and get the answer for omega square. Then we will get B. B is gamma by 2M. So 0.05 by 2 into 0.5. So we have got B also. Then get F naught. F naught is capital F naught by M. So 25 by 0.5 is giving us 50. So if you get all these three values, we can simply substitute in this formula and get the answer. So how we are going to substitute? F naught we have got as 50. So in place of F naught we have put 50. And omega naught square is what? 2000. So in place of omega naught square we have put 2000. And P square, in place of P square we are going to substitute 2 omega naught square. 2 omega naught whole square I can say. So we are writing 8000 plus 4b square p square. Simplify, you are getting the amplitude which will be in meters because it is an SI system. All the given quantities are in SI system. So we are going to get the answer also in SI. So after amplitude, we'll also have to find the phase shift. So what is the formula for the phase shift? Phi is given by tan inverse 2 bp upon omega naught square minus p square. So for p, we are going to write 2 omega naught because it's twice the natural frequency. So it will be 4b omega naught. So we have minus 4 into 0.05 upon omega naught square minus 4 omega square will be minus 3 omega naught square. Anyhow, we have the value of omega naught square. So write the value and get the answer. So phi is equal to 0.085. So with this, we will stop and we'll continue our discussion in the next class. Thank you and see you again in the next class.
Like, share and subscribe. Hit the bell icon for more updates.